Now 3.4, it will teach us a strategy to educate against zeros of polynomial functions. So please understand how important it is to be able to find all the zeros of a polynomial function, because you can see from 3.2, those zeros tell us where the x-intercepts are, right? If you have to graph it. Not to mention, if you're able to graph a polynomial function, that means there's nothing that you don't know about that function anymore, right? That's how important it is. Not to mention, do you remember back in college algebra how hard it might be to solve a higher order polynomial equation, right? I mean, everyone knows how to solve a quadratic equation, which is a degree 2 polynomial equation. But when it comes to the cubic, quartic, right, degree 4, degree 5, 6, 7, it will be almost impossible for you to just do it by hand. But nowadays, do you see this completely no point of solving equations by hand anymore? Even before the AI, right? Well, at least that we have TID4, we have Desmos. Do you remember how you will normally solve an equations with TID4 or Desmos? If you would do that in SAT, you guys know that, right? Just type up the equation in the calculator, let it graph, and look for the x-intercepts. And it does not only work for the polynomial equation. It works for any equation. Therefore, you probably don't see any point of learning some fancy rules, which is known as the rational zero theorem. But at least that, it could sometimes be, a sanity check, or, you just have to show me your understanding in some of the questions in the test. Right. Anyway, so let's see what the rational zero theorem says. For any polynomial function of degree n, but its coefficients, a sub n minus 1, right, all the way down to a sub 0. All those numbers multiplying those variable terms, right, those coefficients. If they're integers, you can guess the rational zeros by looking at only the constant a sub 0 and the leading term a sub n. Sorry, not a leading term, leading coefficient a sub n. What you have to do is you're going to get all possible factors of the constant and also all possible factors of the leading coefficient a sub n and divide them, and it will provide you a lot, right? But it will provide you all possible rational zeros. So you're going to have a whole list that you can do educated guess. Okay. I know that sounds pretty abstract, but if you have seen it before, that's very straightforward. But if you've never seen it, let's demonstrate that with, an example, which I don't even bother to do it in front of you, just that's why, I take the screenshot from the book. Let me emphasize that we are looking at all possible and rational zeros. First off, you know that zeros are x-intercepts. They are the solutions to an equation, right? Just by setting the polynomial function to 0. But is this a rational zero? Is it? It's not even rational. Do you see that? But can it be a 0 for a polynomial? Yes, but it's not rational. So you're never going to get a 0 like that from the rational zero theorem. Okay. Now what about this guy, 1/3? Is it a possible rational 0 for a polynomial? Yes, because it's rational, right? Because rational is basically fractions. Okay. Not to mention 0.3 repeating. It's rational because 1/3 is 0.3 repeating. Now, what you do is you take that constant, -2, and you come up with all possible factors. Do you see that there's always going to be a factor of 1, right, for any numbers? But do you see that 2 has only 2 factors, 1 and a 2? But if it's -2, not to mention positive 2, do you see that if 1 is a factor of 2 or -2, is -1 also a factor of 2 or -2? Well, how do I know if the factor 1, 2, 3 is indeed a factor of a number? Or just in case, because you're probably going to hear me saying factors all the time. So my question could be, is 7 a factor of 343? Okay, so not just knowing whether or not 7 is a factor, you do know how to figure it out, right? Just by dividing 343 by 7 to see if you get an integer as a quotient, basically no remainder, right? And that's when we made a factor. So now, a number as easy as -2, does it have a factor of 1? Yes. Does it have a factor of -1? Yes. 2 divided by -1 is an integer, right? Does it have a factor of 2? Yes. -2? Yes. Do you see that? It doesn't matter whether it's 2 or -2. You just look at the absolute value and come with all possible integers that might be a factor. Then you need to include both positive and negative, possibilities. So now I hope that you understand. -2 has 4 possible factors: positive 1, plus or minus 1, plus or minus 2. Now, what about 15, which is the leading coefficient? Are you able to convince yourself that 1, 3, 5, even 15 itself are the factors of 15, right? Including the negative versions. So now, how many possibilities are you looking at? The factors for the numerator, you have 4 possibilities, right? The denominators, you have 8 possibilities. You need to divide every single possible factor on the numerator by every single factor on the denominator to form a possible rational zero. Then how many rational zeros are you supposed to have in this case? Well, of course, you can see how many are there, right? But 4 different numerators divided by 8 different denominators. How many different fractions could you form before simplifying them? Do you see that you get 32? 4 times 8. So, 18, because I overcounted. Do you see that? Positive 1 divided by positive 1 is the same thing as -1 divided by -1, right? Here's how you can count it. Forget about the plus and minus. The number of factors on the top, the 2 of them, right? Numbers on the bottom, 4 of them. 2 times 4, you get 8. Double it because you're always going to get a positive and negative. But still 18, right? That means you're looking at close to 20 possible solution, possible zeros. And since there's only a couple of them, might be right. But at least that it's not infinite many. So that's what people came up with a couple hundred years ago. Say that we don't have calculator, we don't know how to graph it, right? So at least that we have a list of possible rational zeros we can check, right? So now here's the part that maybe will seem completely pointless at this moment. Let's try to find all the zeros. That means including irrational. But they want you to start with a guess. but you can do a random guess, right? Since you get that list from the rational, zero theorem, right? And in this case, if you look at -6, it has 4 factors, right? Including a plus and minus, right? In total 8, right? So 4 numbers on the top, right? 1, 2, 3, and 6. But for the leading coefficient, the good news is it's only 1, right? So now, how many zeros are you supposed to have? Rational-wise, you have 4 possibilities over 1 possibility. 4 times 1, you get 4. Double it, you get 8 possible rational zeros. That means you're supposed to check all 8 of them to find at least 1 to start with, right? Okay, you know what? They say, how do you check whether, say, 1 is a rational zero, or 2, or -1? They say, why don't you do the division, just like you did over here, right? How do you know a factor indeed works out for a number? They say divide. Divide the polynomial f of x by a factor. I don't know if it's right there. Yeah, over there. Divide that polynomial by a factor x minus whatever rational zero you thought is going to work, and use the synthetic division. And you hope that you're going to get a zero remainder. But the problem is, remember that this whole rationale is behind the what they call it, the remainder theorem. If you remember that from 3.3. But listen to the question one more time. How do you know 1 is a zero for f of x? Is there a better way to tell? If you already know what f of x is, it's x cubed plus 2x squared minus 5x minus 6. You can plug in 1 for x and see if the function is indeed 0. Does it make sense? So, I mean, like I said, if you have to show me, or if I demand that you show me using a rational zero theorem and the synthetic division to find out at least 1 zero that works out and go from there, then you're going to show me everything. That's why I have it out there. But you should get me a 0, start from the top of the list, right? Just by plug them in. And now, let's try in the calculator. You guys have the TI-84? Take out the TI-84 and let's type up the function. And I want to make sure that you guys don't end up typing up the whole thing over and again, going back, changing the x to something else. Let's use the function in the TI-84 to make the process a lot more efficient. Okay, so now first off, you're going to hit the first button on the top left, where it says y equals. You're going to specify a function, and you get to choose from y1 to y9. It doesn't matter. Let's go with the first one. Let's type in exactly this function, right? So you're going to have to put in the x, right? So what you do is you see the button where it says like a recall, right? Or send it to, right? There's an x there, but it's in green. That means you're going to go alpha x, right? But now I need to take that to the third power. Let's take that third power. Okay. Now we add 2x squared, right? So 2, let's find x, alpha x, right? 2x squared. Let's do square minus 5x minus 6. Okay, hit enter to store this function, right? Then exit out. If you want to exit out, just go second quit. So now, how do we call the function? So if it's TI-84, I'm not sure about ID3 or maybe the older version. If the TI-84 CE, find a button where it says vars. That means variables. Right there, variables. Hit it. Then you go to the second tab where it says y variables. And the first option, functions. And again, hit it once, to recall F1, right? Y1, that's what we typed up. So now I need to evaluate the function at those possible zeros, right? So you see that we have a list of -1, right? +1, -1, +2, -2. Let me start with the 1. How do you evaluate a function? You need to include that number you want to evaluate in a parentheses, right? So Y1 already typed up, open parentheses, put in a 1, right? If you want, you can close the parentheses, but you don't have to. Hit enter. It tells you what f of 1 is. Is 1 a 0? No, right? Now, I need to check as many as I can, right? But I need to find the first one at least. Don't retype the Y1 by going through all those like buttons and options, right? Use the arrow, go up there, pick that option, right? Highlight it, hit enter, right? Then go back and change the number to -1, right? But don't do minus, right? Do -1, -1. You don't have to close the parentheses, to be honest. Hit enter. Oh, it works. -1 is a 0. You see that? If you want to try it again, you don't have to, because all I need is at least find 1 0. Go back up, right? Highlight this guy. Hit enter, right? Copy and paste. Change the number to 2. Hit enter. Oh, 2 is also a 0. Right? Make sure you're able to do that. Or if you have a better way, let me know. Because this is what you should do to evaluate. Yes. You could, but if you have to show me this way, that means at least you should pretend that you get me a 0. That way, start from it, factor it. But that's what exactly I'm saying. Nowadays, who does that by hand? You're gonna graph it and find all the zeros. But remember that they didn't have that, back then, right? But now, just like Cecilia just said, you should know the zeros no matter what, right? But now you have to figure it out what you have to do about them. Okay, but you should never miss those zeros. But like I said, by all means, graph it. But right now, let's say the reason why I insist that you have to get at least one of the zeros to start is a degree 3 polynomial. We want to solve it by factoring. And if we already figured out that 2 is a 0, right? You saw that 2 is a 0. Using the remainder or the factor theorem from 3.3, we know that this polynomial must be factorable, and that must be a factor in a form x minus 2. You guys remember that from 3.3, right? But now the question is, how did it figure out the rest part? And you know what? It's like asking you, what is the quotient if you divide 343 by 7? Well, you just divide it, right? And the same thing here. You divide this polynomial by this degree 1 divisor, and you see how nice it is. This kind of divisor is always going to be degree 1, and it has a leading coefficient 1, and you can do the synthetic division. Again, you probably don't see any point of doing it since you already know what the zeros are, but FRQ is going to say use the synthetic division and factor and solve the equation. Therefore, I'm assuming that you know how to do that by dividing the polynomial by the x minus 1 using the synthetic division, find out the remaining quadratic part. And when you get to the quadratic part, do you know that it's always factorable, right? But of course, if you want to guess like what might be the 0, start from there, do the synthetic division. You could, but I think that most people will actually do what they call the AC method kind of thing, right? Break down the 3 to 3 and 1. They added to before. Therefore, just by factoring the quadratic trinomial, it will be x plus 3 times x plus 1. Okay, and like I said, unfortunately, you need to show me that you're able to factor it like that in FRQ. Right? But think of this. If, for example, Sashara already saw there are 3 zeros, right, from a calculator. There's a 2, there's a -3, there's a -1. Do you think that you can actually construct that factor form without actually factoring it? Since you know it has to be factored like that, right? But we'll get to that, in a second. And of course, once you get a factor form, use the zero product principle to find out what the zeros are. Okay. You guys with me so far? All right, so I have like 10 minutes. Now let's do one problem seriously. The same way. I know that's not really that informative anymore, right? But look at this. It's a degree 4 polynomial, even though the instruction doesn't say that you have to do it a certain way, but that's not from the question bank. All right, so the test problem is going to say you're going to use factoring, you're going to use synthetic division, right? Use the rational zero theorem to find out all the zeros or to solve that polynomial equations. Okay, so that means I'm expected to see that, in FRQ. So let me make sure that you're able to do that, even if you already know what the zeros are. All right, so first off, let's come up with a list of all possible zeros, all possible rational zeros. Okay, so I'll say rational zero will come from a huge list, right? So it goes to the top, all possible factors of 24. Does 24 have 1? Yes, right? What about 2? 3? 4? Not 5, right? 6? 8? 12? And 24. You guys agree with that? That's all the possible factors of 24, right? Plus or minus. I'm just listing all possible factors. I'm not trying to add or subtract them. Okay? So there are 8 options, right? So now the good news is the leading coefficient is 1. That means we'll be plus or minus 1, right? Now, how many possible rational roots, rational zeros should you check? In principle, you have 8 options. 1, so that means you're looking at 16. Okay. But do you see that you should start from 1 over 1 plus or minus 1, 2 over 1 plus or minus 2, 3 over 1 plus or minus 3, right? Dot, dot, dot. But now, to be honest with you, if I have to solve this problem, I don't even bother to write down a list, but you will have to, to show me in a test. But I know that it's almost always going to start 1, 2, and a 3. Because who doesn't have a factor of 1, right? That means the worst case scenario is I check the first 6 easy zeros. If they work out, great. If they don't, I'm probably going to go with the graphing. Right? That's how you practically solve the problem. And you know that those questions from the question bank, they almost always going to have either 1, 2, 3 or negative them to be a 0, right? Now, I'll tell you that what works out in this case. So if you try using the calculator, right, feeding either 1, negative 2, 2, it turns out that F2, if I remember it correctly, let me see, F2 is indeed a 0. So now guess what? The original polynomial, x to the 4th minus 6x squared minus 8x plus 24 must be divisible by a factor of x minus 2, right? But you need to figure it out. What will be the quotient? But I see how quick you guys are in synthetic division, right? So after synthetic division, you will figure that it will be a cubic polynomial, right? It will be x to the 3rd plus 2x squared minus 2x minus 12. Okay, so that's the quotient. No remainders because it's guaranteed to be a 0. You guys follow? Go. Now, what else should I do? I mean, that's still cubic, right? That's not too easy to factor at this moment. But you see what has happened, right? By guessing 1 0, you're able to downgrade a degree 4 to a degree 3, right? You hope to get to degree 2 so that you can always factor it, right? What do? Try another round. That means you're going to start guessing what might be the rational zero for this guy, right? And divide out to see that if we can reach that to a lower degree polynomial. But you know what? Now, guess, could it be plus minus 1, plus minus 2, plus minus 3? And don't jump to the 3, right? So maybe 1's going to work out. And it turns out x equals, let me see, 2, again, is a zero of the polynomial x cubed plus 2x squared minus 2x minus 12. And again, please make sure that you convince yourself after class, 2 is indeed a 0, right? So now what? Do the division once again. Since 2 is still a 0 for this cubic polynomial, you're going to divide it by x minus 2 again, right? And you're guaranteed to reach a quadratic polynomial. All right, so after synthetic division, it turns out to be x squared plus 4x minus a plus 6 equal to 0. Okay. So when you get to the quadratic, you don't have to factor it anymore. Now, at this point, we have figured out the original function f of x has a factor of x minus 2 for 2 rounds, right? If you want, you can actually write it as a square. But also you have a quadratic trinomial factor, right? So now let's make sure that the degree matches. This guy's degree 2, right? That's a degree 2, added to be degree 4. So indeed, the original polynomial is degree 4. So now do you know how to find a 0? By setting it to 0 and find out what possible x's you get. How many solutions are you supposed to have for a degree 4 polynomial equation? You must have 4 solutions. Does it make sense? But not all of them are real. You do get a repeated 0, right? X to the 2. But guess what? This quadratic function doesn't have real solutions. But I'm sure you can figure out using quadratic formula, right? It will be 2 complex conjugate solutions. Total 4, right? So you guys figure out the rest. But this is the whole process using the rational zero theorem. Have a list to guess what will be the rational zeros. Start with one of the zeros, do the division, and downgrade the polynomial all the way down to a degree 2. Because you can always solve for degree 2, right? And that's pretty much, what the 3.4 have to be